Our next lecture will be about something that is called wavelet transform. We will talk about definition, properties, and give some examples of the continuous as well as of discrete wavelet transform. So at the beginning, we will start with our motivation. Actually, we will introduce a problem and then we will see, we will seek the way how to solve that problem. Short time Fourier transform is a pretty good tool. It is often used in, especially in speech analysis, in analysis of audio signals, in analysis of biomedical signals. It is really a brilliant tool. You can see how we can say print of your voice in time frequency plane. You can see the basic frequencies as well as harmonics and so on. So it is really amazing tool. What's wrong with it? Why we need something else? That's a question. Nothing's wrong. That's one answer, but let's try to apply it to music. At first, we have to learn something about frequencies in music, in audio signals that contains music or human singing, whatever you prefer. I will share something else. So this is music note to frequency chart. Human ear can hear about 10 octaves. Here we have 8 of them. I just found it on internet. And it is well known that some frequencies are defined, like the tone A is 440 Hertz. But the tone A, if you double the frequency, it is still tone A, but in the next octave. If you halve the frequency and you get 220 Hertz, it is still tone A, but in the lower octave. Or you can do it once again or once again. So 110 Hertz, 55 Hertz, and finally 27, 50. I'm not sure that I can hear that. Maybe you can. Is also tone A. And on the other side, you can see that 7 kilohertz is also tone A. The distance between the tones and the octave 0 in the left hand column is pretty small. Somewhere it is a little bit more than 1 Hertz, but right here it is even less than 1 Hertz. And on the right hand side, on the rightmost column, you will see that the difference between the half tones is almost 500 Hertz. And I said that there are some more, so even. Okay, so let's, in our mind, let us design a system that is based on short time Fourier transform, which can recognize musical tones. Which we have 12 half tones in between the octaves. So actually, maybe we can say that it is, I will just draw how it looks like. So actually, I mean, it was not always like this. The people who are more familiar with music knows that there are several music scales. And let's say the modern one was introduced by Johann Sebastian Bach. The difference between the neighboring tones actually is 12th root of 2. And the the neighboring tones like C, CIS, then D, E, F, GHs. So the difference between them is 12th root of 2, because the octave has 12 half tones, one octave, and the difference between octaves is doubling, so times 2. And then the difference between the neighboring half tones is the 12th square root of 2. Okay, so short time Fourier transform has a uniform resolution over the time frequency plane. As engineers, we have to think about the worst position. So if we want to distinguish C and CIS in the lowest octave, your resolution in the frequency domain must be something like 1 Hertz, at least. Can be better, but not worse than that. If your resolution is 1 Hertz, and if you apply the Heisenberg uncertainty principle, you will easily find that your resolution in time domain will be in seconds. I don't want to say how many seconds, it really depends about your choice of the time window, but if you choose the Gaussian, it could be 10 seconds, something like that. And it is definitely not good enough for music. It seems that Heisenberg Heisenberg principle of uncertainty explains us that it is impossible to listen to the music. Of course, we all know that it's not true. So what is the problem, or how to solve that? I mean, we cannot compete with the Heisenberg principle of uncertainty. It is where it is. But the problem is, I mean, it is an advantage, but also a problem, that short-time Fourier transform has a uniform, once you decide about your time localization window, you actually decided about the resolution in time and frequency domain, and it is constant all over the time frequency plane. The truth is that for analysis of the music signals, we do not need a uniform resolution. We need something different. I will bring back that screen with the frequencies. We can easily see that we have a logarithmic frequency axis. Maybe the easiest way is to look at the row that describes tone A. So 440, 800, so doubling the frequency after each octave, or halving the frequency after each octave. And logarithmic scale in frequency. That is what is missing. So that is how it works, how our brain and our ear can hear the tones. Definitely, we do not have a linear frequency scale. We have such a logarithmic frequency scale, and it really corresponds to the tones on the piano, or on guitar or any modern instrument. Okay. So let's go back to our presentation. So, since we cannot beat the uncertainty principle, maybe we can just go around. Instead of having constant resolution over the time frequency plane, maybe it would be a better idea to have different resolutions for different frequencies. We need pretty high precision when the frequencies are very low, And we have to accept that in that case, resolution in time will not be very nice. But on the other hand, we need pretty good resolution in time for high frequencies, and we don't care about frequency resolution in such an extent for the, let's say, right-hand octaves on the piano. So that brings us to another idea. Instead of, I will change the camera again. Instead of having such a uniform resolution, instead of having, let's say, we are going to leave the idea that our transform must look exactly like Fourier transform. E to the j omega was cosine and sine, so something that lasts forever. Maybe we don't need such a wave that lasts forever. We don't need something like this, the big wave that started at the beginning of the universe and ends up at the end of the universe. Instead of that, we can have a small wave, and we are going to call it wavelet. Small wave can look like this. It can look like this. It is something that is localized in time and probably localized in frequency. It is wavy. Actually, in French language, it's called ondelet. The original name for wavelets were ondelet. So it comes from some guys that actually were in area of geophysics, and they started with that wavelet transform. So this will be our wavelet function, something that is denoted as psi on the slide. So when you see psi, you can think about a small wave. It can look like this, for example. It can be rectangular, of course. It can look like, it can be triangular. Or it can be maybe a Gaussian multiplied by sine and cosine, and it can look like this. Okay. But it is localized in time. Instead of shifting it in frequency, we are going to expand it, stretch it, or compress it or expand it. That is what we are going to do. So if you want to move some function to the left or to the right, you add that tau. Tau means shift to the left or to the right. But if you want to expand or compress some function, then we introduce the scale. Scale is something that we put in denominator. So if you have some function like this one, and if you say psi of t over 2, what have I done? I just make it longer. I made it longer, okay. 2 times longer than this one. Okay, but the red one has more energy than the blue one, so I need some constant in front, that's here. So to make the red one and the blue one to have the same energy. And that brings us to a transform that looks like this. So instead of shifting the frequency, we are kind of expanding and compressing the function. We are still moving it to the left or to the right. This is the normalization term, and altogether is called continuous wavelet transform. The result has two dimensions. It has one dimension more than the original one. It definitely depends on the chosen wavelet. We can choose this one, or that one, and the result will not be the same. Now we forget the cosine and sine. It doesn't have to do anything with cosines and sines. It can do, but doesn't have to do. We expect that the chosen function, chosen wavelet, mother wavelet, provides what we want. It has desired properties in both domains. So we are going to expand it, to stretch it, and actually compare it to X to get our wavelet spectrum. Scale A is somehow reverse proportional to the frequency, because the longer signal is slower, it corresponds to lower frequency. Shorter signal is faster, it corresponds to higher frequency. So in this A is not a frequency, it is something that is reversely proportional to the frequency. And now we ask our standard questions. Where is that function in time and frequency domain, and how big it is? I will go a little bit faster. I will just show you the slides. So if you calculate the energy concentration centers, you will, after some time, you will see that it depends on scale A, not only, the center depends on tau and A as well. After some substitution, you will see that this does not belong to this slide. Something is wrong on the slide. I have to correct it, but I'll do it later. So the position of the center depends on psi, but also on the chosen scale. Here is the result. So of course it is linearly proportional to the tau, as it was in the short time Fourier transform case, but also it depends on scale, especially if it's not symmetric. If it's symmetric around zero, then we have the same equation as before, at least if we are talking about time shift. Let's go to the scale or frequency shift. Right now, the shift in time domain corresponds to exponential part in the frequency domain. Scale in the time domain corresponds to, it is reversely proportional to the frequency in frequency domain. And when you do all the calculation, you will see that this constant is also reversed. So right now we are calculating where we are in the frequency domain. And you will see that the relation is definitely not linear. It is not linear at all. It depends on scale, and scale is in denominator. Looks like this. So definitely it is not linear, but it looks like dividing by 2, multiplying by 2. So it is definitely logarithmic. So let's put it together. So effective width in the time domain was looking like this. Effective width in the frequency domain was looking like this. Both of them changes. So the effective width in the time domain changes depending on scale. Of course, it changes. The red one is wider than the blue one. If A equals 2, of course, it is wider. Or vice versa. If A was 1/2, it would be shorter. Okay, what happens in the frequency domain? In the frequency domain, you have something similar, but reversed. Which means that the product of the two will be constant. The product of the size in time and frequency domain will be constant, but they change at each point of the time frequency plane. The centers are linearly proportional to the shift tau, and definitely non-linearly dependent on the scale A. So if I have to draw my ellipses, it would look like this. We have better resolution for lower frequencies than for some higher frequencies, if we are talking about resolution in frequency domain. In time domain, it is exactly the opposite. We have much better resolution for higher frequencies than for lower frequencies. And if you recall some piece of music, you will easily notice that it is very difficult to play something very fast using left hand on your piano. So fast pieces of music are mostly related to high frequencies, and that is the way how our brain is working as well. Our brain also has very, very precise resolution on low frequencies and very, very high resolution in time for high frequencies. So instead of having uniform resolution, now we have non-uniform resolution. So the result can be adjusted to the properties of music. It looks like what to choose for our wavelet function. I just had some proposals right here, but instead of having cosine and sine, we can have only cosine function. It's called Morley wavelet. You have a Gaussian multiplied by cosine functions. It's a real Morley wavelet, and this guy would be complex Morley wavelet. They can be used easily for analysis of the music, and this is one thing that you will do by yourself in MATLAB. We can use the second derivative of the Gaussian, which is actually called Mexican hat, because it looks like Mexican hat. Also, this is a kind of a wavelet, a small wave, time-limited wave. It is time-limited. It is limited in time, but also in frequency. And maybe we can compare the two on the same slide. I'm going to use a piece of paper just to illustrate what are we talking about. So if we want to compare the short time Fourier transform, which is actually on the right hand side, this slide. So short time Fourier transform used cosine and sine multiplied by the Gaussian. On the right column, second row, you see one possible variant of such a thing, but only the real part is drawn. So we have some Gaussian, invisible Gaussian. It multiplied cosine and sine signals as well, but sine is not here just for the simplicity. So we have a real version of STFT. Okay, so in STFT, the window, which is actually G of t, does not change. It is always the same. Doesn't matter about the frequency. Here the frequency was 1. if it's 2 or even if it's 1/2, what happens? If it's 2, you will have more waves inside, but the width will be the same. Or if it's 1/2, you will have less waves. It could have looked like this. So that's STFT, and our localization window, the red one, defines the properties in both domains. They are unchanged all over the plane. So what happens with continuous wavelet transform? I mean, I could choose, I can choose many different windows, but right now I'm going to choose this one for my wavelet. So if my scale is equal 1, the result will be the same as here. I mean, among all possible wavelets, this one is also okay. So I'm using this one to make a comparison. So what happens when the scale goes to 2 or to 1/2? Notice that it is reversely proportional to frequency. So what happens here? If the scale is equal to, this guy will be expanded to double size, but it will be longer, 2 times longer than this guy. These guys were all the same size, and this guy will be shorter, 2 times shorter. You have something which is actually the same, only expanded or compressed. So this is the basic difference. So in this way, we can cover, for example, if you choose scale 2, 1, and 1/2, you are jumping to the neighboring octaves. But if your step is much smaller, if it is a 12th root of 2, then you are jumping over neighboring half tones, and it can be adjusted to the properties of the music, of the piece of music. So here is how it looks like in the frequency domain. So STFT does only linear shifts. The width in frequency domain does not change. But here, for continuous wavelet transform, the width changes. What was wider in time domain, now it's narrower in the frequency domain, and vice versa. But the product remains the same. Here, the product, of course, is the same because they are constant and they do not change, and the product is, of course, constant. So, if we analyze our 2 signs with, for example, Morley wavelet, we are going to get such a result. We have a better resolution in the frequency domain for lower frequencies, and a little bit worse resolution for higher frequencies, but for higher frequencies, we have that tails in the spectrum, and that tails enables us to very precisely detect where the observed phenomenon has started and when it ended up. Okay, so we have very precise localization in time due to high frequency component of the observed phenomenon. In the same time, we have a good frequency localization, especially for low frequencies, so we can have them both in a way going around to the Heisenberg principle due to non-uniform resolution in the time frequency plane. Okay. Now, of course, our next question is there an inverse formula? Yes, there is. We have to integrate over all shifts, though, over all scales. The scales are positive numbers, so notice that a little difference in the boundaries. Okay. How to know whether our wavelet was admissible for does it preserve information? Is the inverse formula possible or not? This constant can be calculated using this equation, and this equation brings us to the conclusion that DC component must be 0 because we have denominator of 0, and numerator must be 0 as well. Instead, if we want to get the definite constant, which means that in all of my examples, I suggested some wavelets, but the very important things is that they have no DC component. So let's say the positive area was always equal to the negative area. It was the admissibility condition for every choice of wavelets. So we are not allowed to choose wavelet functions that contains some DC shift. That's what is written right here. And finally, all the things together are right here. So this is the equation for continuous wavelet transform. This is the inverse formula. And yeah, it contains this constant, and this constant can be calculated this way. And this is a kind of admissibility condition for the CWT. How to calculate it in practice? We can calculate it using, of course, different shifts in time domain, but in the Fourier domain, it corresponds to filtering. We can have a bank of filters for different scales. The result is, again, convolution. I'm just going fast because I know that on the one hand, you are not able to follow all that equations and slides, but still you can understand what are we talking about, and there is a lot of similar things to the STFT. The only difference is that we still have a bank of filters, but that filters are not of the same size. They are not the same. They are not only the shifted versions of one filter that just repeats itself. Instead, we have non-equals filters in the bank. So if I can just draw, if I can just make a sketch of STFT filter bank, it would be a set of equal filters. You apply the same signal to all of them and they are just shifted. Okay, I will not draw the rest for simplicity. Okay, so we have a uniform filter bank. In case of wavelets, you have a non-uniform filter bank. If our filter bank is about the analysis of music, if you want to make a technical systems that can recognize what notes were played, in that case, the difference between filters will be very small. I mean, by the 12th root of 2. but they will be more and more narrow when we go to lower frequencies. On the slide, you can see octave filter bank, where scale goes from 1 to 2 to 4. On the other side, it could be 1/2, 1/4, and so on. And we can implement actually the continuous wavelet transform as a non-uniform filter bank. Of course, it would be technically more and more complex to make more and more narrow filters in our attempt to realize the continuous wavelet transform. How about the discretization? And this is our last topic for today. Instead of having linear scale, right now we have a logarithmic scale. Yeah, for example, for analysis of the music, the difference between the neighboring halftones is 12th root of 2, which means that, for example, our A0, our beginning scale, is 12th root of 2, and then we choose the powers of that number. So we are going, k is from the set of integers, okay? If k equals 0, this is 1, then k equals 1, 2, 3, 4, it goes over the halftones inside of one octave, and when k becomes 12, so we have 12 power of 12 root, which means 1. So we actually doubled the scale, and so on and so on. So we must have some number that goes to the power k. And what happens to our shift tau? It has no sense to have linear discretization of the tau, because our functions are of uneven length. Here they were all equal. Right here, this one, I mean, it corresponds to low frequencies. So your jump can be longer than definitely here. We have a very short wavelet, and here we need to have a dense quantization of the time scale. And it is actually, so our quantization must be, m is some integer, must be proportional to some constant, but multiplied by the actual scale. So if the scale is smaller, it must be denser. If the scale is bigger, it can be, you can make a longer steps. So this is the way how to discretize the CWT. Here is the result. The result is called discrete wavelet transform. Notice that the spectrum is discrete. M and K are integers, but actually the signal is still continuous, and our wavelet is also a continuous function. So T is from the set of real numbers. So a non-uniform quantization of the TF plane is sketched or illustrated right here. This illustration corresponds to the choice where A0 equals 2. So it would not be good enough for the analysis of music, but it is pretty good enough for many applications. And many people think that this is the only way how to discretize the continuous wavelet transform, because such a transform is mostly can be realized with fast filter banks, and it is used in compression, in digital cinema standards, and as well as in analysis of images. And it also corresponds to convolutional neural networks. I mean, in some way. This is that famous frame condition, which is out of scope of our course, but I'm just mentioning it for completeness. And yeah, if our A0 equals 2, if we jump over octaves, we have we can design a fast realization using filter banks, and that is our next task, but for the next week. At the end, I will just use the last minutes to ask you, how about next week, Thursday? Is it okay with you, or you have some other proposition?
Thursday is good for me.
Okay, how about you, Melissa or Maxim?
Same
It's
for
good
me.
for me too.
Okay, then see you next Thursday. We will also have a package of 2 lectures together, and this is the way how we can go on and cope with all that stuff. At the end, please tell me, was it understandable? I mean, were you able to follow the stuff?
Yeah, I think so.
Yeah, I mean, I know that we were a little bit faster at the end, but still, it's not about understanding each and every slide, but let's say the basic principles and the motivation. Why are we doing that, and why is it so useful in analysis of speech, like short time Fourier transform, or in analysis of music signals and other audio signals